So for evaluating limits analytically, you're just going to be using your skills in mathematics to simplify things down generally and come up with a real answer. Take a look at these limits. The limit as x approaches 2 of 3 is what? Seems tricky. It's 3. The number 3 right here is my function, basically. Okay? The limit as x approaches 2 of 3. Does 3 care what x is doing at all in this case? Not at all. Okay? So it's just 3. It's like the constant function y equals 3. That would be a horizontal line that goes through 3 on the y-axis. Doesn't matter what value x is, it's always going to have a function value of 3. The limit as x approaches negative 4 of x. So we could think of that as being the function y equals x, and now I'm taking the limit as x approaches negative 4. What am I going to get? Negative 4. The limit as x approaches 2 of x to the third power. So you can think of that as y equals x to the third power. What do we get as we approach 2 with x? What are you doing each time? Basically, you're just substituting in the limit, okay? And you're able to do that because what is not happening here? We don't have division by 0. So when you do that, it's called direct substitution, and we'll get to that in a little bit here, apparently. So one of the most confusing parts of calculus is the notation. It's the language that you have to learn in order to be successful in the class. Learn the language, you're going to be more successful. Don't learn the language, you're always going to be confused. So this is sort of like the first time you're going to see formal calculus notation in this class, and just get used to it. Understand what it means, read it correctly, so that when you see it, you don't get lost. Okay, we have let b and c be real numbers. Let n be a positive integer. Let f and g be functions with the following limits. So the limit as x approaches c, and we know that c is some real number. We don't know what number. It doesn't matter. It's just a number. Of my function f of x is equal to this capital L, some value. So if I have some function here, I evaluate the limit as x approaches c. Of that function, I get some limit as an answer. Okay? In general. The limit as x approaches that same c of my g of x is equal to some other value k. The important thing here to notice is that it is approaching the same number. X is approaching c in both cases. So the first property we're going to talk about is the scalar multiple. Scalar multiple, if you think back to geometry, the word scalar kind of works with like scale factor. If you're multiplying like a triangle times a scale factor of 3, you're basically dilating it to be 3 times bigger than it was, right? Scalar multiple is just a constant that you're multiplying onto something. So if I have the limit as x approaches c of my function f of x, but now there's that b in there too, it's just a scalar multiple, and I can pull that b out, evaluate the limit as I had already done, and then put the b back in, and I wind up with b times L. So I'm just multiplying the limit by that same scalar. If I have a sum or a difference, in other words, if I have the limit as x approaches c of two functions being added or subtracted, I can split that into two separate limits. The limit as x approaches c of f of x, I already know. The limit as x approaches c of g of x, I already know. L and k. If I'm adding, I would have L plus k for my limit. If I'm subtracting, I would have L minus k for my limit. Where this comes in handy is for something like a polynomial. Y equals 3x squared plus 2x or something. This is the property you're going to be using here. I can now evaluate the limit of each of these terms as x approaches some number, rather than not know what to do. The product, if I have two functions that are being multiplied together and I'm finding the limit as x approaches c, and I know the limit of each of these functions already, the limit will just be those two limits multiplied together. Likewise with the quotient, if I know the limit of f of x and g of x as x approaches c, then it's just going to be one limit divided by the other. And the power rule. I better not call it the power rule. I don't know what I want to call it, but we have something called the power rule in calculus, and I don't want to call this the power rule. But if you're working with a function that's raised to a power, and you're taking the limit of that known function, the limit is also just raised to the power, and you'll have your answer. So these properties are important to remember. The notation looks tough, but if you understand what it means, then it kind of simplifies down to something that's fairly easy, I think. So how do we use these properties? We'll come up with strategies here in a little bit, but just straightforward properties, and these are some of the homework type problems in your book. We have the limit as x approaches 2 of 4x squared plus 3. What can I do? If I use these properties, then I can say that I have the limit of two functions being added together, y equals 4x squared and y equals 3. Those two functions are kind of being added together if you think of it that way. So I could rewrite this as the limit as x approaches 2 of 4x squared plus the limit as x approaches 2 of 3. I can go even further with that, and I can say, okay, I have a constant out here, so I can pull that out front and write 4 times the limit of as x approaches 2 of x squared plus the limit as x approaches 2 of 3. Then I can go even further and say that I have x squared sitting here, so if I knew what the limit as x approaches, let me write this down. Limit x approaches 2 of x squared plus limit x approaches 2 of 3. And now I have something raised to a power here, which means if I knew the limit of x as x approaches 2 of x, then I could find that, and then I could raise it to that power, and then I could multiply it by 4, and then I could add whatever this is. Right? Basically, all we're doing, by the way, what would the limit as x approaches 2 of x be? 2. And then 2 squared would be, and then 4 times 4 is, and then what would the limit of this be? So 16 plus 3, 19, right? What are we really doing here? We're just doing something called direct substitution. Because the function actually exists at this limit when x is approaching 2, because the function actually exists at 2, there's no need to worry about whether or not the function is continuous. We know that it's continuous there. So we can just direct substitute. And when you do that, you get 4 times 2 squared plus 3, which is exactly what we have written here in a much longer and more painful version, right? So 2 squared is 4, 4 times 4 is 16, 16 plus 3 is 19. You're not always going to be able to direct substitute. So being able to use these properties is an important skill. But in this case, we could, so we did. And we get to the answer much faster. Okay, evaluate the limit. We have the limit as x approaches 1 of x squared plus x plus 2 divided by x plus 1. All right, yeah, sure. The function is discontinuous at x equals -1, right? Is that what we're looking for here? No. So, could I just plug 1 in and use direct substitution? Does the function exist at 1? Is the function continuous at 1? Yes. The only place where we have a discontinuity is -1. But we're not looking for x is approaching -1. We're looking for x is approaching +1. The function is continuous there. So we can direct substitute. When we do, we get 1 squared plus 1 plus 2 all over 1 plus 1. So we have 1 plus 1 plus 2, that's 4, over 2, which is 2. We're already tired? Is the function discontinuous at 0? No. So I can direct substitute, and I get 2. Is the function discontinuous at 3? No. So I direct substitute. 3 squared is 9. 9 times 2 is 18. 18 minus 10 is... And then what's this 3 right here mean? The cube root of 8 is... Okay, maybe the toughest one, right? Cosine is continuous. So that means I can just direct substitute with pi. Cosine of pi is... It's -1. And then we have this x out front, so I get -pi. So here's our formal trig function limits. I'm going to make your day and tell you that the ones on the left, sine, cosine, and tangent, those are the ones we're going to generally be working with in this class. Occasionally, we'll work with secant, cosecant, and cotangent. Later on this year, we'll work with them a little bit more, but for the most part, sine, cosine, tangent. This is pretty straightforward stuff. If I direct substitute c in for x, I get sine of c. Same thing for cosine, and really the same thing for tangent. The only thing about tangent is we have to be careful of vertical asymptotes. All right? Because remember, tangent is actually not continuous. What is tangent? It's sine over cosine. So when would the vertical asymptotes be occurring in tangent? When the cosine is equal to 0. What about cotangent? What's that one? Good. So in this case, then the vertical asymptotes would be occurring when sine is equal to 0. And up here, cosecant is 1 over sine, and this one is 1 over cosine. So when sine is 0 or when cosine is 0, we'll have vertical asymptotes here and here. So we have to watch out for that, but that's not going to pop up too much, so I wouldn't worry too much about it. Make sure you know the ones on the left. So we can direct substitute with trig functions. What is the limit as x approaches 0 then of tangent x? The best way to do this, my suggestion, is to split tangent into sine 0 over cosine 0. I'm direct substituting, but I'm using my trig identity for tangent. 1 on the bottom, 0 on the top, so this is 0. No. You're finding a limit, right? So then the limit does not exist because you're approaching a vertical asymptote. Okay, limit as x approaches 0 of sine squared x. First of all, we need to remember what this notation here means. What does sine squared x mean? Yes, it means after you get whatever sine is, then you square it. So I could rewrite this as the limit as x approaches 0 of sine x being squared. Once you do that, now it's easy to see if I direct substitute the 0 in for x. I have sine 0, which is 0, and then 0 squared is 0. This notation right here needs to be something that you can work with instantaneously without thinking about it. Make sure you recognize what that means. We're going to work with it all year. All right, strategies for finding limits. We haven't talked about two of these yet. We know the top one, direct substitution. That's your number one strategy. Try to direct substitute. If you can, that makes the problem very easy. If you can't, then you have to use either the dividing out technique or the rationalizing technique. All right? So we've learned this one already, and next is going to be the dividing out technique. The funny thing is you already know it. You just don't know that you know it. So the strategy is check to see if direct substitution can be applied. If not, then you need to find a new function that agrees with the original function at all points, except the limit. That's going to be involving the dividing out or rationalizing technique. So what you're doing is you're creating a brand new function that has, if you were to graph it, exactly the same graph with the exception of that discontinuity, so that now you can actually evaluate the limit. Then you're going to evaluate the limit analytically and then confirm your answer using a graphing utility or a table, just to make sure that what you're doing is correct. So that's sort of our way of making sure that you understand what's going on. All right, so the dividing out technique. Find the limit of this function as x approaches negative 3. Take a look. Can we do direct substitution here? No, why? You get division by 0, right? Negative 3 plus 3 is 0. So if you notice down here, when direct substitution yields 0 over 0, so we know we have over 0, but we didn't know that we had 0 over 0. When that happens, there's a factor that can be what we call divided out. So let's check this thing. Let's substitute in negative 3. When we do, we get negative 3 squared plus negative 3 minus 6, all divided by negative 3 plus 3. Well, negative 3 squared is 9. 9 plus negative 3 is 6. 6 minus 6 is 0 over 0. So we do get 0 over 0. This is the check that you're going to have to do when you do if direct substitution is going to fail. Check to see if you get 0 over 0. If you do, that's called the indeterminate form. It means that something can be done to it to create a brand new function that is the same in every way as the original function, except for that one discontinuity where you're trying to find the limit. So to do the dividing out technique, you're going to factor the numerator and the denominator if it can be factored. So how can I factor x squared plus x minus 6? What am I looking for? Two numbers that what? Two numbers that multiply to give you C and add to give you B, right? We have two numbers to do that. What are they? Plus 3 minus 2. All divided by x plus 3. Okay, so you see it. We have the limit as x approaches negative 3 out front still. So now we can see that there's going to be something we can divide out. It's the x plus 3's. Notice I'm not saying whatever that word is that you guys like to say all the time. That's not what you do. You're dividing out. It's now gone. Limit as x approaches negative 3 now of x minus 2. Can we take that limit using direct substitution? Yeah, we can. So when we do that, we direct substitute and we get negative 3 minus 2, which is negative 5. So that's the answer. The dividing out technique is so called because we have something that is dividing out, leaving us with no longer this division by 0 here because of the limit. And now that there is no division by 0, we can evaluate the limit. So to finish what we need to do here on this problem, we need to graph this function right here. All right, so here's my calculator. I'm going to graph this thing in a second, but just before I graph it, I know that you have all graphed it at this point. Did you expect to see what you saw? What did you expect to see? You expected to see a parabola, but in fact you got a line. The reason you got a line is because once we divide out, we're working with the line, basically, y equals x minus 2. And if you look at this graph, it does appear to cross through at negative 2 on the y-axis and have a slope of 1. Okay? The difference is, bring up the table now. So with my table up here, I can see that as I approach negative 3 from the left side, so from the negative side, I'm approaching negative 5, but when I get to negative 3 I'm undefined. Same thing is true coming in from the positive side. I'm approaching negative 5, but when I get there, I am undefined. Okay? So there is a hole in this graph. Even though it looks like a line, there is a hole there. The only way you would know that is if you did a little analysis with your negative 3 and direct substituted. Now let's graph our equation y equals x minus 2. So when you graph it, you should get exactly the same graph. I did not graph it on top of the other one. Hopefully some of you did. You can graph it directly above or directly on top of the other equation. And you see that sometimes the calculator might show you like different colors, but it is exactly the same graph. You can bring the table up to show two different columns, and it will have exactly the same values with the exception of where it was undefined. Your original function will be still undefined, but your new function will have a value there. And the value that we get is what? Negative 5. So the analytical approach gives us negative 5 using algebra, using the dividing out technique. The graphical and numerical approach shows us that we have the exact same graph in both. The numerical approach shows us in those two tables that we are approaching the same value in both of those equations from both sides. It's just that now this one actually allows me to evaluate that function at that number. All right, so that was like half of the techniques that you need to know. We'll do hopefully some practice problems here pretty soon. Using the rationalizing technique, this is the other method that we have. Find the limit. So again, if we want a direct substitute, can we? No, we can't. You plug 0 in, and clearly there's division by 0 here. But if we try to do the direct substitution for the top and bottom, then we get the square root of 1 minus 1 over 0. The square root of 1 is 1. 1 minus 1 is 0, so you get 0 over 0. Again, we have the indeterminate form. We can't use the dividing out technique here, though, because there's no way to factor what you see in the numerator. We're going to have to come up with something. There's some way that we can get, basically, the result will be an x that divides out. So technically, you will be dividing out eventually. But in order to get there, you need to use what we call the rationalizing technique. You have to rationalize the numerator. You learned how to rationalize in Algebra 2. You did. To rationalize something, you have to do what? Conjugate. Yep. You're going to multiply the top and the bottom by the conjugate. But in this case, it's going to be of the numerator. So, fancy one. Multiply the top and the bottom by the conjugate. Let's set that up. We have the square root of x plus 1 minus 1 over x. Now my fancy one is going to be the conjugate of the numerator. So that will be what?
Square root of x plus 1.
Plus 1 divided by, oops, you messed me up, thanks. The same thing, it's a fancy one. X plus 1 plus 1. Okay. So let's take care of the numerator. This is 2 terms times 2 terms, which means we are going to FOIL. We have the square root of x plus 1 times the square root of x plus 1, which becomes x plus 1. It's actually a fairly easy one to deal with. Now, because we're dealing with conjugates and we're FOILing, what happens? The difference, the O and the I disappear. Right? If you don't remember that, we're going to have the O term. 1 times the square root of x plus 1 is positive square root x plus 1. Negative 1 times the square root of x plus 1 is negative square root x plus 1. You put those together and they drop out. That's the beauty of conjugates. The O and the I in FOIL disappear. So now we just need to multiply the L, which is negative 1, divided by, how do we deal with the denominator? The answer is we don't. This is x times this stuff, and we leave it as x times this stuff. What happens in the numerator? The ones add to 0, and I'm left with x over x times square root x plus 1 plus 1. Now what happens? We divide out the x's. What am I left with in the numerator? 0? 1. Okay? So now we can simplify that. We're done with the rationalizing technique, and technically we did divide out here, but it's rationalizing that gets us there. So I'm going to rewrite the problem now in terms of what we have. The limit as x approaches 0 of 1 over square root x plus 1 plus 1. Once something has divided out, you can now take the limit. If you didn't divide something out in either of these methods that we have, then you still will have division by 0. Substitute in 0, and we have square root of 1 plus 1, which is 2, so it becomes 1/2. 1/2 is the answer. So as I'm checking on my calculator, I have the graph. It looks like kind of an upside down square root function. I can see that as I approach 0 from the left, from the negative side, it appears that I'm approaching 0.5, which is 1/2. If I scroll down, if it will let me scroll down, I don't want to scroll over. I want to scroll down. There we go. It does look like I'm approaching 1/2 from the other side, okay? And we do have that discontinuity sitting right here. Now what I want to do is enter in the other function, the one that we just came up with after we did the limit. And I want to enter that as a new function in this window. It'll be the first time I do this on this calculator, so let's see if I can do it. Okay, so now we have our original function f1 in blue. We have our red function f2 in red. And if you look at the decimal places that are happening here, we have exactly the same thing. The only difference between these two functions is that our original is undefined at 1/2, or sorry, at 0. But our new function that we had some algebra done to is giving us that 0.5, which is what we came up with algebraically. So we do have exactly the same function, with the exception of that hole. The hole is filled in our new function, which allows us to get that 0.5.